Okay, hello everyone, and welcome to today's lecture. Uh, I have shared my screen. I hope you can see it and you can hear me clearly. If not, please let me know. Okay, so last time we were talking about branch and arithmetic instructions, and we also talked about how we can use the branch instructions to implement loops. For example, the do while loop. We had a look at a couple of examples, but we were left with one more example to complete this set of slides about the branch instructions. So let me do this example, or let me walk you through this example, and then we can continue with our set of slides for today. So let's say we want to write a program which calculates the sum of all odd numbers from 1 to 27. So note here that we are not adding 2, we are not adding 4. So we are adding only odd numbers. So how can we do that? So again, the best way is first always to write your pseudocode or to draw the control flow diagram and then convert it into the assembly program. So if we look on this control flow diagram, we are first putting the value of 0 in R20 and we are putting 1 in 16. So what we can do is basically that we can hold or we can put the result of addition in R16 and then we can increment R20. Actually, we can use any one of them, but in this example, we are incrementing R16 and we keep incrementing it until it reaches the value of 27. Until it is less than or equal to 27, we keep doing the loop, and once it becomes greater than 27, we end the loop. So in the body of the loop, what we are doing is we are adding R20 and R16. So initially we have 0 plus 1. So we are actually putting 1 into R20. And then the register which carries the value of 1, we are incrementing it, but by a value of 2. So we are adding 2 to the register because we want to add only the odd numbers, not even numbers. So then R16 will become 3 next time because earlier it had value of 1. So when you add 2, it becomes 3. And then you check, is R16 less than or equal to 27? If yes, go back to the body of the loop. If not, exit the loop, right? So let's have a look at its equivalent assembly program. So the initialization is easy. We are simply using load immediate instruction to put value of 0 in R20 and value of 1 in R16. And then we are entering the body of the loop. So here our loop is starting. That's why we are putting L1 here, right? So we are saying first add R16 and R20 and then increment R16 by 2 and then compare R16 by 29. Why we are comparing with 29? Basically, the next number you will have in R16 after 27, it will be 29. So if your R16 becomes equal to 29, you can break the loop, right? And if it so, mm, again, if you want, uh, I can rewrite the condition in a different way, but necessarily saying the same thing. What does it mean? So what we can do is that instead of we can compare R16 against 29, right? So because when we want to add up to 27. So we can say that if R16 is equal to 27, then uh, don't go back to the loop, right? So what we can do is that we can say, actually, we can have this condition rewritten. We can say like if uh, until it becomes equal to 29, then keep looping. And once it is equal to 29, then don't go back into the loop, right? So here we can say if R16 is equal to 29, then go back to the loop. Sorry, uh, then, sorry, break the loop, right? Break the loop. Else, go to the loop, go back to the loop. So remember, last time I said that we always in assembly, most of the time, we prefer to write an instruction which does which checks the condition opposite of what we have in our pseudocode. So here we are saying if R16 is equal to 29, right? So we can say, we can in assembly we can say branch if not equal to 29, then go back to the loop. So this is opposite of, right? But does exactly the same thing. We are saying, here we are saying if R16 is equal to 29, break the loop. And here we are saying if it is not equal to 29, then go to the loop. So we are doing this thing, right? So here we keep incrementing, and when the value comes equal to every time we add 2 to the value of R16 and then compare with 29. And when we say, okay, if it is not equal to 29, go back to L1. But if it is it has become equal to 29, then don't go back and go to the next instruction in sequence, which is here, right? So this is how you can convert this control flow diagram into the equivalent assembly program. And what will be the value of offset? RK, it will be -4 in this case. Why? Because PC plus 1 is pointing to this next instruction after branch not equal. So how much offset we need to go back to the L1? 4, because you can count simply 1, 2, 3, and 4. Okay. Any questions? No? Okay. So last time we have talked about like in last lecture and the lecture before that, we talked about status register, and we also talked about that our branch instructions which we have covered until now, they basically check your carry flag as the zero flag. For example, when you say branch if same or higher, or when you say branch low, or when you say branch equal or not equal, you are either checking zero flag or the carry flag, right? So zero flag is enough. A zero flag and carry flag, they are enough when you are comparing the unsigned numbers. But when you want to do the comparison for signed numbers and then want to take a branch based on the result of comparison of those signed numbers, then carry flag and the zero flag, they are not enough. So let me first again give you a quick reminder about signed numbers and unsigned numbers, and then we can come back to the slides again. Yeah. So uh, let's say I'm writing this 8-bit binary, and you need to tell me like whether, okay, let me first write the binary. Uh, Maybe let me write a very 4-bit number, because then it takes less time to explain things, right? So let's say I'm writing this 4-bit binary, right? So assume we have 4-bit registers. So if I ask what is the equivalent decimal value for this bit pattern, what will be your answer? You can unmute yourself, or you can put your answer in the chat box. What will be the decimal equivalent of this 4-bit binary? Okay. Someone said, actually, more than one student, they said 11. 11 in decimal. right? Anyone who has a different opinion? Anyone who has different opinion? What if I say that, mm, no, I don't agree with you, and 1011 is equal to uh, -5? Anyone who has same opinion that this is equal to -5 in decimal? Say yes or simply type. If you don't agree, even then say I don't agree. Don't agree. You are not like, you have multiple options. Okay, so the thing which I'm trying to demonstrate is this. Numbers, by looking at numbers, bit patterns themselves, you cannot tell them whether they are signed or whether they are like signed numbers or unsigned numbers. It all depends upon the person who is interpreting those numbers, right? So if I say like I'm interpreting this bit pattern as unsigned, then it is equal to 11. But if I say that no, I'm interpreting this bit pattern as signed number, then value is -5. Now remember that if I decide to interpret a bit pattern as signed number, then most significant bit has a negative weight, right? So if it has negative weight, it will be -8 plus 2 plus 1. So it will be equal to -5, right? So when you are dealing with unsigned numbers and you want to compare them and these numbers, like for example, unsigned numbers where you consider that your most significant bit is not representing the sign, it has positive weight. If you are dealing with unsigned numbers in your programs and you want to compare them and then want to take a branch based on the comparison of unsigned numbers, then you can use these instructions like branch same or higher, branch low, branch equal, branch not equal, and so on, right? I'm not writing all of them, right? But if you are dealing, so what are the examples of like real life examples where you need your numbers to be only unsigned, which means they will be always positive. For example, if you are writing a program which deals with the ages of the people, or which deals with the number of students in a class, or it deals, let's say, with the height of the people. So all these values, all these parameters or characteristics can always have only positive values, right? You cannot say that age of a person is -10 or height of a person is -2, right? But if you are dealing with some other characteristics, let's say you talk about the your bank balance or amount you have in your bank account, it can be positive or it can be negative, right? So in that case, you will be dealing with signed numbers. So if you are comparing, let's say, two bank accounts and then you want to take a branch based on the result of comparison, you cannot use these instructions. Why? We will talk about them later. But you can use other instructions which are used, which are meant to compare the signed numbers. Okay. I hope what I said is clear to everyone. If not, please let me know. Okay. So So these flags, NVS and flags are meaningful only for signed numbers. So when you are using unsigned numbers, carry flag and Z flag, they are enough when you want to compare them. But they are not enough for comparison of comparing signed numbers. And therefore we need extra flags which are already available in status register. And these are your your negative flag, overflow flag, and sign flag. Okay, so let's say that X is the true result of an instruction. So true result mean that what it should be, right? So we are referring to it as a true result. So N flag tells us that the actual result is one which we have in our register. It could be the true result, it could not be. Like it depends. We will see. Okay. But actual result can be possibly different from the true result. But the true is one which we should have mathematically, right? So N flag will tells us that the actual result which we have in register is negative. And if N is equal to 1, uh, So it's mean that most significant bit of the register is 1. So it is simply n flag is simply uh, duplicate of the most significant bit of your register, register holding the result. Okay. So if most significant bit is 0, n will be 0. If most significant bit is 1, n will be 1. So the problem with n flag is that that what does it tells? It tells us that okay, so n flag tells us that the result in the register is positive or negative, right? So if it is 1, it's mean result is negative, and if it is 0, that it's mean the result is positive. However, the uh, the value of n flag does not represent the correct status when an overflow happens. Okay. So what is overflow? So overflow, it happens when the value of a result or an operation, it is actually less than minus 128 or greater than 127. Why? Because and we are talking about signed numbers, right? And if we have an 8-bit signed numbers, what is the range of the values we can represent from minus 128 to 127, both minus 128 included and 127 included, right? So if the value of the result is out of this range, it's mean the overflow has happened and the V flag will be set equal to 1. But if the value is within the range, then it's mean there is no overflow and V is equal to 0. But the thing is, like, if overflow happens, then we cannot trust the N flag. Then N flag represents the incorrect value. However, if the overflow flag is 0, there is no overflow, and V flag is 0, uh, then we can trust the negative flag or N flag. Okay. Sign flag. Sign flag is actually exclusive are of both flags, negative flag and our overflow flag. So actually it is like correct, it is the corrected version of the n flag. So again, as I said, if there is no over flag, we can trust the negative flags, and it is telling us the correct value. But if our flow happens, then the value of 0 or 1 for n flag has no meaning. We cannot trust it. So if we cannot trust it, it's mean we need an alternate way which we can trust all the time, whether our flow happens or not, to tell us whether the value stored in the register or obtained in the register is positive or negative. And that flag is sign flag. Okay, and how it is computed, it is basically exclusive are of both n and v. So if s is equal to 1, then it's mean that our value is negative, it is less than 0 in the register. And if s is equal to 0, then it's mean that value is positive in the register. So whenever we are comparing signed numbers, we will always trust the sign flag. Okay. Any questions? We will see examples and then it will become more clear to you uh, how we use the S flag. If you have any questions, please stop me. So negative flag, I have already explained what is its job, but then we cannot trust it all the time, especially when overflow happens. The value represented by the information conveyed by negative flag is may not be correct. Okay, so here let's have an example. Let's say we want to add these two numbers, 96 and 70, right? So when we add them together, I don't want to walk you through the addition process. You can do it on your own. But when you will add, you will see that the most significant bit, the bit at this position is 1, right? Now remember that n is simply a copy of the most significant bit position. So it means that n is equal to 1, right? So it means that result is positive. The result is negative because n is equal to 1. But we are adding 96 and 70. So the result is 166. So the result is supposed to be positive, right? The result is supposed to be positive, but our n flag is telling us that the result is negative. Why? Why it is giving us the wrong information? Because our flow has happened. How we know our flow has happened? Because the result of the addition is 166. And what is the range of the signed numbers, 8-bit signed numbers, from minus 128 to 127? So 127 is 166 is greater than 127. So our flow has happened, and that's why we cannot trust the negative flag, that's why you can say that negative flag is conveying us the wrong information. Okay, any questions? So uh, flag v overflow, it actually indicates that whether the overflow of signed arithmetic operation has happened or not. So v flag is set. I mean at the at like human level, like I am doing here the addition in decimal system, right? So if I do that in decimal system, I get 166 and I know that it is out of the range. That's why the overflow has happened. But how does the hardware knows that how does the hardware detects whether the overflow has happened or not? So or how does the hardware set v equal to 1 or 0? So the v is set to 1 if and only if either of the two following two conditions are true. One of these two conditions is true, which is like if there is a carry from D6 to D7 in our destination register, or there is a carry, or again there is a carry from D7 out, but no carry from D6 to D7. So one of these are happening like if there is a carry from D6 to D7, but no carry out of D7, or there is a carry from D7 out, but no carry from D6 to D7. Okay. So let's have a look at a couple of examples. Again, we exactly have the same numbers which we were adding last time. Is it same? Are the same numbers? Yeah. So 96 and 70, right? So when you add these numbers together, so here you will have a carry from D6 to D7, but no carry out of D7, right? So uh, it's mean that now our flow has happened. So if our flow has happened here, since our flow has happened, we cannot trust the n flag. So we will, in order to check whether our result is positive or negative, we will look at we will look at our sign flag. Okay, and sign flag is basically the exclusive OR of negative flag and our flow flag. So one exclusive OR one is 0. So sign flag is 0. Okay. So our result is positive. Our result is supposed to be positive, but here it is shown 1 minus 130 when you convert this one into two's complete when you use the two's complement form, right? But otherwise our result should be positive because we assume that we are adding the signed numbers. Another example, everything is same. We simply change the data. Like instead of adding like for example, what was this? 96 and 70, we are adding minus 128 and minus 2. So in this case, there is no carry out of D6 into D7, but there is a carry out from D7. So which means that basically one of these condition is true. This one, this condition is true. Second one. So there will be an overflow. So we cannot trust n flag, but we need to look at the uh, S flag. Okay. So which is telling us that the result is negative. Okay. Someone has, what happens if both conditions are true? So if both conditions are true, then still again we will be sorry, the sun flag will be set. Why? The overflow flag will be set. Why? Because we said that at least if one of them is true, our flag will be set. So if both are true, so we are meeting the condition, which is requirement of fulfilling one condition. So if both are true, still our flow flag will be set equal to 1. Okay, so here are some other examples like how the overflow flag is set. In this case, we don't have we have carry from both from D6 into D7, and we have a carry out of D7. Like for both cases, there is a carry. So we said V equal to 0, right? Again, let me go back here. So we said that there is a carry from D6 to D7, but no carry out of D7. Or there is a carry out from D7, but no carry from D6 to D7. So both of these conditions are not true, right? Though both of these conditions are false because we are having a carry from D6 to D7 and we are also having a carry from out of D7, right? And again, this is also false. So that's why V flag is not set to 1. So V is 0. So it's mean we can now trust in this case, your N flag is conveying the correct information, but and your sign flag is also conveying the correct information. So what I'm trying to emphasize here is that when you are comparing the sign numbers, your sign flag conveys the wrong information all the times, irrespective of whether there is an overflow or not. But your negative flag, you cannot trust it in all cases, when especially there is an overflow. Okay, so we don't care for N flag. We will look at always at the sign flag. Here is another example. We have no carry from D6 to D7 and we have no carry out of D7. So V is equal to 0. And here we have no carry out of D6 into D7, but we have a carry out of D7. So our V is equal to 1. So we cannot trust N, but as always, we can trust S. Okay. Any questions? I don't know if I can minimize this thing or not. Let me check. Okay. Okay, comparing signed and unsigned numbers. So again, this is like uh, going back to the same point which I explained earlier while I was writing on OneNote, that if you are comparing A and B, and if A and B are considered unsigned, again, it all depends upon your interpretation of the bit patterns. If you are interpreting them as unsigned numbers, then you can use branch low and branch same and higher to compare the numbers, and then take the for example, compare the numbers, and then based on the comparison, you can use branch low and branch same and higher to take the action, to take the branch, right? Because they rely on the C flag, right? And these are unsigned numbers. However, if A and B are considered signed numbers, which mean when you look at the bit pattern, you consider the most significant bit to have a negative weight, then you cannot use branch low and branch same or higher, because now the carry flag will not give you the correct information. For the correct information, you need to look at the sign flag. And therefore, for comparing the signed numbers, you need to use branch less than and branch greater than equal to instructions, because these instructions, they actually take the branching decision based on the value of the S flag, not on the based on the value of the C flag. Remember, BRL0, branch low and branch same and higher, they take branching decision based on the value of the carry flag. Okay, so they check the sign flag in S register, and sign flag is, as I said, exclusive OR of negative flag and the overflow flag. So here is just the truth table for the sign flag. So it is just an exclusive OR operation. Okay, I don't want to walk you through this table. Okay, so here are some examples which actually shows you that in all, so here on the in the first two columns we have two numbers, and then we are doing like subtraction A minus B, because remember, the comparison operation, it performs the subtraction, and then based on the result of the subtraction, your flags are set, and then your next branch instruction checks one of those flags. For example, if it is branch same or higher or branch low, then it will look at the carry flag. If it is branch equal or branch not equal, it look at the value of zero flag. And if it is branch less than or branch greater than equal to, it will look at the value of the S flag, a sign flag, right? So when you are doing these operations, so there are cases where you can trust the value of where C will convey you the right information. Carry flag will give you the correct information. What does it mean? If you remember from the last lecture, we said when we are subtracting A minus B, then by the carry flag tells us that A is same or higher than B when the carry flag has value of 0, and A is less than B when value of the A is sorry, the A is less than B when value of the carry flag is 1, right? So here 10 is less than 8, so carry flag is 0, right? 10 is greater than 8, so which is like same and same or higher. So carry flag is 0. Here 8 is less than 10 in the second part. So we can carry is telling us that okay, the value is 1, so it's mean it is conveying the good correct information. Next time in the next -2 -1, so carry flag is, what is carry flag? It is 1, so it is telling us that A is less than B, which is true, right? -2 is less than -1. And next line C is 0, which means that carry flag is telling us that uh, A has same A is same or higher than B, right? So A is -1 and -1 is higher than -2, right? So C is conveying the correct information. But now when we come to this the next line, this line here, so C is telling us that value is 1, value of C is 1. So when you do the subtract operation 2 minus 1. So when the value of carry flag 1 is 1, it means what? It's mean that A is less than B, but A is 2 and B is -1. So A is not less than B, which means that carry is conveying us wrong information, right? So actually I have, yeah, let me, oh, sorry, I have that example already. So where is that table again? Yeah, so we were at this point. We were at this point, right? So let me walk you through the example where we actually subtract 2 and -1. So here, not this one. You can go through this one on your own. I like just included them in the slides, but I don't want to walk you through all of them because it will take time. We can go through the example which has case of, yeah, this one, right? A is equal to 2 and B is equal to -1. Now, if I convert into the binary, so binary of A is this one. If I convert -1 into the binary and I'm using signed numbers, so it will be all ones. And again, I'm using 4-bit, I'm assuming 4-bit register or 4-bit binary because if I use 8-bit, it will take too long time. So here when you do the A minus B, so you get this result, right? So which is equal to 3. Now if based on the result and the operation, you set the values of the flag. Carry flag is set equal to 1 because we have here carry in the most significant bit position. Our flow is equal to 0 because our value is within the range, and sign flag is equal to 0 because sign flag is what? Sign flag is your exclusive OR of our flow and the n flag. N flag is what? N flag is the most significant bit of the result. So 0 exclusive OR 0 is 0, right? But the issue here is that C is equal to 1 is telling me that A is less than B. But A is equal to 2 and B is equal to -1. It's mean that A is not less than B, right? So we cannot trust C flag because we are interpreting bit pattern to be signed. However, we can trust this flag when if we had interpreted the bit pattern as signed numbers. So let's do that example where we interpret these bit patterns as signed numbers, which is shown here. So 0010 is 2 and all 4 1 is 15, not -1, because most significant bit, it doesn't have the negative flag, a negative weight. So you have 15, and now when you do the math, so you come up with the result of 1 1, right, in binary. I'm not saying that 2 minus 15 is 3, but because we cannot show -3 in the unsigned representation, so we only have 3, right? So but here, at least in this case, carry is still 2. We have carry in most significant positions, so carry is equal to 1. And what it is telling me, it is telling me that A is less than B, and in this case A is equal to 2 and B is equal to 15, which is true because we are considering bit pattern to be unsigned numbers. So the point I'm trying to highlight is that we can trust carry to convey the correct information only when we are only when we are using the signed unsigned numbers, only when we are comparing the unsigned numbers. But if we compare signed numbers, we cannot trust the carry flag all the time. Okay. So yeah. Any questions at this point? Or am I going into too much detail and I'm boring you? I don't know. If you think like I am explaining things extra, like I'm wasting your time and I sound redundant, let me know. Okay. So again, there is another example where carry value is 0, which basically mean that A is greater than same or higher as B, but that is not true here because A is -1, so it is less than B, which is 2, right? So we cannot trust. Again, if you want to do, you can do exactly same procedure as I showed you in the slide, and then you will see that, okay, the carry flag is set equal to 0, right? Uh, Okay, let me do this interesting example. So we have seen couple of example where carry flag is conveying the wrong information. Now let's do the last example where we see that both carry flag and the sign flag both convey the wrong information, right? But in all these cases, the point which I want, which is like the main takeaway of this slide is that in all these operation, you can always trust the sign flag because it gives you the correct information. Okay. So let me go to that last part. Yeah, here 127, right? So here A is -127 and B is equal to 2. So if I convert A to like I want to calculate the binary of -127, how? First I calculate the binary of 127, then take its one complement and then add 1 to it. So it becomes this one. So -127 into its complement form is this one, right? B is equal to 2 and I simply convert it into two-bit binary, so I have this number. Now I do A minus B, and when I do, I don't want you to like, I cannot uh, explain the whole subtraction process. You can do it on your own, but you will see that you get this 8-bit number in result, right? So here carry is 0. Here we don't have carry in this most significant position. There is no carry, right? So carry is 0. So it is, what does it tell me? When carry is 0, it tells me that A is greater than or equal to B, which is false. Why? Because A is -127 and B is equal to 2. So carry is giving me wrong information. It is conveying wrong information. However, V flag is equal to 1. Why? Because there will be there is a carry in from like D7 into D6, okay, or borrow in, you can say borrow in from D7 into D6. So V flag is equal to 1, and even like if you are adding, if you are saying -127 minus 2, so you should have result of -129, which cannot be stored in a 8-bit register using signed representation, right? So the overflow will be equal to 1, and N flag is equal to 0. This is your N flag, right? But what is N flag telling me? N flag is telling me that the result is positive, which is not true. Because when you say -127 minus 2, you get 129, which is negative. So it is telling me that result is positive, which is false. As correct result is -129. So, but when I look at sign flag, which is computed as exclusive R of overflow and N, I get 1, which is telling me that result is negative, which is correct. Okay. Any questions? Okay. Okay, today you guys have quiz tour, right? We still have time. Okay, so with that, we are done with our branching instructions, both which can be used to compare signed and unsigned numbers. So for signed, as I said, you can use branch less than or branch greater than equal to instructions when you are comparing the signed numbers. Okay, so we have already seen covered the add instruction. So here it is only for the purpose of completion. So because we are going to, from this point onward, we are going to talk about arithmetic instructions. So I just wanted to add it for the purpose of like completion. Here we have you have two registers, source and destination. So the addition is performed between them, and the result is saved back in the destination register. Okay, and then and then these flags are set, carry, Z, and other flags are also set. But here we are only looking at the values of these flags, carry, Z, and half carry. Okay. Uh, the main focus of this slide is just to convey this information that add instruction, it cannot use an immediate an immediate or direct number. So which basically mean that you cannot say add uh, RD with RD register with 25 R, so which is basically you cannot apply give an immediate operand. And direct basically mean that you cannot say using add instruction does not allow you to read one of the operand directly from memory. It is not allowed. So you must read if you want to add a number from memory into a register content, so that number from memory must first be loaded into the register and then added into the destination register. So here is an example. Uh, so assume that RAM location, this one, have the value of 22 hexa, right? So you want to write a program which adds the location of the RAM, value of the RAM location, value of the RAM location at this address to immediate number of 12, right? So first what you do is that you load the data from the static memory from this address into the R2 register, right? And then you add it into the, by using load immediate, you can then you load the immediate number 0x12 into R21 register, and then you add these two registers together, R2 and R21. So you cannot use an immediate number directly in the add instruction, or you cannot read one operand from the memory in add instruction. Okay, so that is like that is what I wanted to focus in this slide. Okay. Uh, Okay, let me first read this statement of this example, and it will actually also highlight the problem we are going to address. So let's say we need to write a program to add two 16-bit numbers, not two 8-bit numbers. Here, when you say add, it is adding two registers, R2 and R21, and both of them are 8-bit, right? So, but this time we want to add two 16-bit numbers. So it's mean that we cannot hold them in one single register, right? So let's say A is a 16-bit number and B is a 16-bit number. So let's say one of that number which we want to add is 0x3b8d, and the other one is 0x3ce7. Each one of them are 16-bit in their width, in their size. So it's mean we cannot hold them in two registers like R1 or R2. So what we are going to do is that we are going to store them in parts. So 8d of like lower part of the first number, I'm naming it as A. So it goes to R16. Its upper half 3b goes to R17, and lower half of number B, which is E7, goes to R18, and upper half 3c is placed in R19. Okay. So we have these numbers now. What we do is that we use two registers to store one 16-bit number. Now we want to add them, and after adding, definitely result will also be greater than 8 bits, right? So we want to store the result in two registers, R18 and R19, such that we place the lower half of the result in R18 and upper half in the R19. Now, how can we do that, right? So basically we want to do this. So we add these two numbers together, but when we add these two lower halves, there will be a carry out from bit 7 into bit 8, and then we should add the upper half of the two numbers also with the carry, right? And to make our life easier, AVR microcontroller give us an instruction which is named as add with carry. So which what we can do is that we can say add 3C, add 3B, and add also, while adding them together, add the value of carry into the addition process as well. So here is the program. We are simply first loading our operands. the lower half of A is loaded into R16, upper half into R17, lower half of B is loaded into R18, and upper half into R19. And then we say first add the lower half. We are doing only this part first, this one, 7, 4. So after adding, so we get the result in R18, but we also get the carry. So next time we say now add R17, R19, and add with carry. So R17 and R19, they actually contain the upper half of both input operands, right? So we are saying add these two, and when we say add carry, so the carry flag, since it was set as a result of the previous addition, this addition, so then it will also be added. Okay. So now we have our full complete result available. The lower half of the result is in R18 and the upper half is in R19. Okay. Any questions? Okay, subtract instruction. Uh, it's straightforward. So subtracting instruction, when you have when you say subtract source register, destination register, then the register becomes equal to destination register minus source register, right? And it also, just like unlike add immediate, it has a variant of sub immediate, which allows you to subtract an immediate number from the from a register, right? So this is the syntax here. K is your immediate number, and the value of the K can be between 0 and 255, both inclusive. And RD is any register from R16 to R31. Okay. Now let's have a look at this example. Basically, what we are doing is we are simply subtracting 3F from 2, 3, right? So how we are subtracting it? So for 3F, we have this binary. So binary of 3, first hexadecimal digit is 30011, and for F we have four ones. For 23, what we do is that we write it in 2's complement. So its binary is this one, 0010 for 2, and for 3 we have 0011. Then we take its 2's complement and we get this number 110111101, right? And here it is already shown 2's complement, right? And then you simply do the addition, right? So because, so remember how we do the subtraction of numbers. We find the 2's complement of the negative number and then we add it to the other one, right? So when you do the addition, you will get this result and there will be a carry out, right? There will be a carry out. However, here they are saying that carry is equal to 0, right? And even here they have written in the statement, notice that there is a carry but C is equal to 0, right? Why C is equal to 0? Although when we do the calculation, we see that there is a carry out in the carry out from the most significant bit, but then why carry flag is equal to 0? Because the AVR microcontroller itself inverts the carry flag after subtract instruction, but not after add instructions. After add instructions, the carry flag will have the same value as you expect if you do the calculation manually on the paper. So carry flag will have the same value. But in case of the subtract instructions, after the subtract instruction, whatever value of the carry flag is, whatever you expect, it is inverted. If you expect it to be 1, it will be inverted to 0. If you expect it to be 0, it will be inverted to be 1. Why? Because then we can use C to carry flag to represent the sign of the number. So if C is equal to 1, after inversion, it means the result is negative. If C is equal to 0, the result is positive. Okay. Okay. There are some other versions of subtract instructions, which are subtract with carry and subtract with carry immediate. So, okay. So here in subtract with carry, you will provide two operands. Like for example, if you want to subtract source register from the destination register, but you also want to subtract the value of carry flag, whatever it is. If it is 0, then 0 will be subtracted. If it is 1, 1 will be subtracted, right? And this actually is similar as subtract with immediate, but with an additional carry, which basically mean that subtract the immediate number from the destination register, but also subtract the carry flag, value of the carry flag. Okay. Okay. Uh, Multiplication. Uh, there are again three different versions of multiplication operation in AVR microcontroller. So let's first look at the simplest one, which is multiply source and destination register. So here both our operands like source and destination, they are considered as unsigned. Like for example, if you are writing a program which deal with ages of the people, and let's say you want to just multiply the ages, then you will multiply, then you will use the multiply instruction, right? So, and after multiplication, your result is because when you multiply, let's say this is 8-bit and this is 8-bit, when you get the product, it can be quite easily, it can be get bigger than 8-bit, right? Unless one of the one of the operands is 1, right? So for example, if you have 8-bit number and you simply multiply 2 with 2, depending upon the value of that 8-bit number, the value of the product can become large enough to be not uh, placeable in a 8-bit register, right? So that's why in all these three multiply operations or instructions, R1 and R0 register is used to hold the result of the operation or a product, right? So R0 used to hold the lower 8 bits of the product, and R1 is used to hold the upper 8 bits. So here is an example. So let's say you want to multiply 150 with 200. So you are loading the immediate values into R16 and R17, and then you are saying multiply R17 with R16. So you will get this result. Uh, and oh, sorry, yeah, this is like kind of confusing because this is decimal. So so then this result will be placed in R1 and R0. So lower 8 bits going to R0 and upper 8 bits going to R1. And you are not, it is not like you need to manually place the result in R0 and R1. No, the hardware on the microcontroller will automatically place the result available in R0 and R1, which means that if you are using R0 for and R1 for some other holding for some other data, uh, copy over that data to some other register or some memory location before doing the multiplication, because otherwise that data will be lost, and then your program can give you some results which you are not expecting. Okay, so this first instruction is for multiplying unsigned numbers. The second instruction is for again for multiplication, but when you are multiplying the signed numbers, right? So both of the input operands are signed, right? So and here you can, for the source register, you can use R16 to R31. So here is an example. Uh, Again, we are using 150 as one of the operand and the other is 10. Now when you use multiply sign, so both these numbers are interpreted as signed numbers. Again, remember, it is numbers themselves, they don't have, like, just by looking at a bit pattern you cannot tell whether it is a signed number or unsigned number. It all depends on the interpretation of the entity who's interpreting their numbers. So if it is a human being, it depends how the human being is interpreting those numbers. If it is microcontroller or hardware, it depends how it is interpreting the numbers. So when you are saying okay multiply s, you are telling the microcontroller that treat those bit patterns which I have placed in R16 and R17 as signed numbers. Okay. So if you are treating them in signed numbers, so 150 will be basically equal to minus 106. So it is representing minus 106 and 10 is representing 10. Okay. You can confirm it by converting 150 into like equivalent binary, and then giving the negative way to most significant bit, and then again converting into decimal. So you will see like it is minus 106. Okay. So when you multiply, the result will be this one, minus 1060. And then this is your uh, this result is in decimal form, right? So 0xFBDC is 2's complement of 1060, right? And then the result, lower half of the result is stored in R0 and the upper half in R1. Last version of multiply signed and unsigned. So this is the case where one of your operand is signed and the other is unsigned. So for example, you use this one when only your source operand is treated as signed number, this one, okay? And this is your unsigned number, okay? And everything else is same. Like for example, you are putting 10 here, 150 here. So 10, even when you assume that the bit pattern is representing the signed number, so 10 is equal to positive 1, positive 10. You can confirm for yourself by converting into binary and then doing the math. So when you multiply, it will be 1500. You convert it into into binary form, hexadecimal form, and the lower half goes to R0 and the upper half goes to R1. Okay. Any questions? Okay. So we have covered basic arithmetic operations like addition, subtraction, multiplication, and the one we are left with is division. There is actually no instruction in the AVR microcontroller by using which you can perform the operation of division. But just like, we can use the repeated addition to multiply two numbers. In the same way, you can use the repeated subtraction to perform the division operation. Okay, so let me try to explain this for you. So let's say you want to write a program where you have like two numbers, one is numerator and the other one is denominator. We are putting numerator in R20. We want to put numerator in R20 and denominator in R21, right? Everyone knows what is numerator and denominator, right? When I'm saying A divided by B, so A is numerator and B is denominator, okay? Quotient is saved and output the as the output of the program. What I want to do is that I want quotient to be available in the register R22 and the remainder in R20, okay? And for that, we can actually write a program where we do the repeated subtraction, and as a result of that repeated subtraction uh, we can get the value of we can get the value of the quotient in R22 and remainder in R20. Actually, let me do this quickly on OneNote. uh, Let me simply copy the program, right? So we have like 5-6 minutes, so I think I can complete it so uh, our uh, let's say we want to do this. We want to say 45 divided by 10, right? So our numerator is 45, which we are putting in R20 register here, right? Our denominator is 10, which we are putting in register R21, right? And then we would like to have our quotient in R22. I'm just writing Q for quotient. And we want to have remainder in R21. No, not R21. Uh, where is the slide? R20. Okay. Okay. Now let me walk you through this program. This one, right? So we have loaded the values. These one. We have cleared the quotient register R20 to 0, right? And now we are saying, okay, increment R22. So this becomes 1. And then we are saying, okay, subtract R21 from R20. Actually, the program is not written in a human in read in a it is not very readable. But anyway, we can do that. So subtract R21 from R20 and put the result back in R20. So we get 35 here, right? And then we are saying branch if carry is cleared. Let me let me change this so that this becomes more readable. Branch same or higher. Okay, I don't want to use branch if cleared because it is kind of confusing. Okay, so we are saying branch if same or higher. What is same and higher? If R20 is greater than R21, right? So yes, but remember that the this branch same or higher checks the carry which was set as the result of this previous instruction, right? So basically we are saying compare 45 with 10 because it was set when the value of R20 was 40, right? When we are comparing 40, we were comparing 45 with 10 here, right? So is 45 same or higher than 10? Yes. So go back to L1. So we go back to L1 and we increment R21 again. So it becomes 2. And then we are saying, okay, subtract again. Subtract 10 from 35. So it becomes 25 now. And then we are saying check if branch if 35 is greater than higher than same or higher than 10. Yes, it is. So we are saying okay, go back to the loop and increment R22, so it becomes 3. And then we say okay, now subtract 10 from 25. So when we subtract, it becomes 15. So then we are saying okay, now here at this branch point, again, compare is 25 same or higher as 10? Yes, it is higher. So go back to the loop here and increment R22, so it becomes 4. And after that, subtract again. So subtract 10 from 15. So it becomes, sorry, it becomes 5, right? And now again, we are saying branch same or higher is 15 higher or greater than same or higher as 10? Yes. So we go back to the loop, increment L1, so it becomes 5. And then we are saying okay, now subtract 10 from 5, so it becomes minus 5. And now we are saying is 5 same or higher as 10? No, it is not same or higher, it is low. So branch is loop is broken, so we come to the next instruction, which is decrement R22. So when we decrement R22, we have 4. And when we say, and then we are saying add R21 into 20, so we are basically adding 10 back to it, so we get 5. So now we have our quotient equal to 4 and our remainder is in R20, which is 5. So basically what you are doing is like you said 45 divided by 10. So 10 for 40 and 5. So 5 is your remainder, 4 is your quotient. Quotient is in R22 and remainder is in R5, R20. Okay. Okay, let's stop here and please go and start doing your quiz.